Okay, so we start this lecture 11 today, which is again on Miller indices. We will continue some part of the previous ones before we move on to the Miller indices for directions. So, last lecture we are talking about Miller indices for planes, and you also have Miller indices for directions. Okay. Now, this is needed to complete the description of the unit cell. So, for plane, Miller indices are usually described as HKL, and for direction you describe the Miller indices as UBW. As we saw that for a plane, the procedure is HKL are nothing but the reciprocal of the intercepts on respective unit cell lengths and which are converted to the smallest set of integers. So, H, K, L all three are integers. They can be positive as well as negative. So, I will just go through some more descriptions of HKL in a unit cell. Okay. Okay. Now, let us say you want to draw a plane which is 1, 2, 3. Okay. So, what you do for that is you go as so this is H, this is K, this is L. So, on x axis your intercept is 1 over 1, on y axis your intercept is 1 over 2, on z axis the intercept is 1 over 3. So, you can see here this is 1, this is half, and this is 1/3, and you can choose this as the origin O because all three are positive. So, if you go in this direction it is plus x, if you go in this direction it is plus y, if you go in this direction it is plus z, and if you connect all three of them, this is your plane 1, 2, 3. Now, suppose you wanted to draw a plane which is 1 bar 2, 3. So, HKL could also be negative. So, this bar 2 means it is negative of 2. So, what this means is that you have intercept along x axis as 1, along minus y axis you have half, and along plus z axis you have 1/3. So, here there is a problem because you now cannot choose this origin, and the thing with Miller indices is that the planes and direction should be represented within one unit cell. You should not be needing to go out of the unit cell. So, in this case what you need to do is that you need to shift your origin. So, if I shift my origin, for example, here I go in minus x, which is not useful to me. I go in positive y, I go in positive z. If I choose my origin here, I can go minus y minus x, but I do not need minus x. So, I choose this as a origin. This is O prime, let us say. So, if I come in this direction, this is plus x. If I come in this direction, this is plus minus y, and if I go in direction 1 above, this is plus z. So, I can now draw the intercept. This is along the x intercept along the A length of the unit cell, which is 1. So, it is at A, this is at half, and this is at 1/3 somewhere here. So, if I now connect these 3 points, so this is 1 bar 2 3 plane. Now, so this is how you, and you can identify a plane if I told you the, as I told you the procedure in the last class, that if you have a plane drawn within a unit cell, now let us say I would want to draw a plane now here. Let us say this is the plane, okay, or let me just draw it in green. This is the one. This is a unit cell whose intercepts. So, if you look at it, now what is the origin you are going to choose first of all? You cannot choose this as origin, it is very obvious here. So, you need to choose an origin from which you can count the intercepts. So, I choose an intercept which is origin which is here, O prime, let us say. So, I have a intercept which is here, which is a, so along x what is the intercept? 1. Along y what is the intercept? Minus 1. Along z what is the intercept? Plus half. Convert it into reciprocal. 1, minus 1 and 2. So, the plane is 1, 1 bar, 2. Okay. So, this is how you draw and identify a plane. So, now another thing is about the family of planes. Okay. So, if I draw a cube, if this is, let us say, if this unit cell is not a, is just a cube, okay. So, just a cube would imply so this is a cube, all right. So, what is this face of the cube? This is 0 0 1. What is this face of the cube? 0 1 0. And what is this face of the cube? 1 0 0. Now, in a cube all these three are identical. So, in a cube 0 0 1, 0 1 0 and 0 0 1 planes are similar planes because of symmetry. If you turn the x axis by 90 degree, then it would look similar to 0 0 1. If you do the rotation of y axis, if you do the rotation of z axis by 90 degrees, all of them will look same, right. So, I can represent these as 0 1 0 0 planes by these curled brackets, okay. So, this would mean a family of 1 0 0 type planes, but only valid for a cubic system, okay. So, 1 0 0 here would mean it implies 1 0 0, it implies 0 1 0 and it implies 0 0 1, okay. So, you can see that you have, so likewise you can have, So, you can see that there is a multiplicity, right. So, in case of cube 1 0 0 implies you also have bar 1 0 0, 0 1 1 0 0 and 0 0 bar 1. So, you have depending upon how you look at it, there are 3 different types of which are identical. 3 different planes, I mean it is sort of oxymoron in some sense. I can just say 3 planes which are identical. Okay. Similarly, if you look at 1 1 0, 1 1 0 would imply 1 0 1, 1 1 0, 0 1 1. It would also imply 1 0 bar 1, 1 bar 1 0, 0 1 bar 1, and you can make some more combinations out of it. So, I will just leave them to you. So, these are called as family of planes, and this is, so if you look at the number of planes here, this is called as multiplicity of the planes. So, in a cubic system, if you look at just 1 0 0 type, it is 6 planes, but crystallographically speaking it is 6 planes if you include the negatives into account. Okay. Similarly, if you look at HH0, you have HH0 will have you have 12 of them. So, you can have 1 0 1, 1 1 0 and so on and so forth. You can have bar 1 0 1, you can have bar 1 1 0 and 0 bar 1 1, and you can have bar 1 0 bar 1, bar 1 bar 1 0 and 0. So, there are 12 of these. Okay. Similarly, if you go to HHH, which is nothing but let us say 1 1 1 kind of plane. So, 1 1 1 would mean 1 bar 1 1, 1 1 bar 1, bar 1 1 1, and you will have other options as well, 1 bar 1 bar 1, bar 1 1 bar 1 and bar 1 bar 1 1, and so you have in total of 8. So, you have 8 multiplicity. So, similarly for a cube, if you take HKL, HKL kind of planes will be 48. If you look at HHL, it will be 24. If you look at HK0, it will be 24, and so on and so forth. Okay. So, this is for cube. Okay. Now, if I do the same exercise now in a tetragon, let us say I take a tetragon. Okay. So, this is the tetragon. So, here A is equal to A is not equal to C. Okay. So, A is equal to B is not equal to C. So, you have 2 lattice parameters A and C. So, here now which one is so this face is this is 0 1 0, this is 1 0 0. Now, what is this? 0 0 1. Now, this plane of course, because of tetragonal symmetry is different as compared to the other 2 planes. This has a 4-fold, these 2 have a 2-fold, and in terms of atomic density, in terms of spacing, it is different. So, in case of tetragonal system, so this is tetragonal, okay. So, in case of tetragonal, 1 0 0 and 0 1 0 are equivalent, but 0 0 1 is not. So, in case of tetragonal, you draw H 0 0, multiplicity will be 4. This will imply H 0 0, 0 H 0, and then you will have 0 0 L. This will have a multiplicity of 2. So, 0 0 L and bar L. Similarly, there are other planes as well. So, when you have HKL or HK0, so HK0 will not be equivalent to H0K or 0 HK, okay, because of tetragonal symmetry, because the third indices is along the C axis, which is C lattice parameter, which has different length as compared to A and B, and things become. So, you can see the multiplicity will go down in tetragonal system, and you will also see that D100 and D010 are same, okay, but D001 is not same as D100 and D010. So, the formula that we saw, D is equal to A divided by square root of H square plus K square plus L square, this is valid only for tetragonal. So, this is DHKL. For tetragonal system, this DHKL would be 1 over square root of H square plus divided by A square, K square divided by A square plus L square divided by C square. So, this is for tetragonal. If you look at orthorhombic, it will be so, now formula looks fairly similar for these three are orthogonal systems, okay. Orthogonal systems. For non-orthogonal systems, these are different, DHKL are different, and I will refer you to principles of X-ray diffraction by B.D. Kaliti. So, at the back there is appendix on these planar interplanar spacings as well as interplanar angles, okay. So, if you look at interplanar angles, they will also be different, they will not be the same, okay. So, similarly you can also look for interplanar angles also have different relations, okay. So, this again you can find in Kaliti, okay. Now, so this is about the tetragonal system. Now, if I go to now directions, so here we have finished the plane part, okay. So, what we have learnt is how to draw a plane, how to determine a plane, how to basically the Miller indices, of a plane which is drawn, how to find the interplanar spacing, and how to find the interplanar angles. So, interplanar spacing, so D100, D010, D001 are all same for cubic. In case of tetragonal, D100 is same as D010, but it is not same as D001 for tetragonal. In case of orthorhombic, and things are even different for other planes, other systems. So, this is just for orthogonal systems. Similarly, angles in case of tetragonal system, in case of cubic system, we saw the angle was cos theta was 1 over H1 H2 plus K1 K2 plus 2 divided square root of H1 square plus K1 square plus into square root of plus K2 square plus L2 square. This is again only for cubic system. It will be different for tetragonal and orthorhombic system. Now, let us go to what we call as directions. Okay. Now, directions are nothing but vectors, all right, and they are denoted as I said earlier, denoted as U, V, W. So, basically we call, a lot of people also call them as crystallographic directions. Okay. Crystallographic directions. So, basically so it is nothing but a vector. So, you resolve the components, so resolve the vector components and then along the crystallographic axis and then reduce them to smallest set of integers. Okay. So, let us see how we work along this. So, you have a, I will again draw a unit cell. One thing that I forgot to mention is that representation HKL is independent of the crystal system. The multiplicity may change, but how you determine a plane, how you draw a plane, that is independent of the crystal system. Okay. So, that is applied to all the crystal systems. As long as you have a unit cell, 3D unit cell, you draw a plane identically in identical fashion, irrespective of type of the crystal system. Okay. So, if I draw a crystal direction, this unit cell, okay. So, let us say I want to draw. So, if I take U, V, W as 1, 2, 3, okay, then what basically it means is that you have one intercept along x. So, this is one translation, one lattice translation along x, two lattice translation now, as opposed to plane, it is not half, it is 2 of lattice translation along. So, basically what this means is that, and this 3 of along z. So, basically it is 1 of x plus 2 of y plus 3 of z. That is how you will represent a vector, right. If it was a vector r, that is how you will represent a vector, right, 1 of x plus 2 of y plus 3 of z. The problem is If you want to draw in this fashion, you will have to go once. So, this is origin, let us say O, you will have 1 here, then you will have to go 2 steps in sorry, this was Y, this was Z. Then you will have to go 2 steps here, and then you will have to go 3 steps, 1, 2, 3. So, you will go out of the unit cell. That is not desirable. What we want to do instead is, what I can do is that I can convert these back to, so if I have 1, 2, 3, I divide it by the largest integer, which is 1 by 3, 2 by 3 and 1. So, what I now do is that, so if I now do 1 by 3rd in x direction, 2 by 3 in, let us say, y direction, and somewhere along here, if I do, hang on, here somewhere here. So, this will be coinciding with this point somewhere here. Okay. So, this is 1/3, 2/3 and 1, and now you connect the end point. So, this is A, this is the direction OA. So, OA is nothing but 1, 2, 3 direction, alright. So, this is the direction. So, direction, a single direction is determined by these square brackets, and family of direction is given as one U V W. So, this is single direction, this is family of directions. Now, let me now take a few more examples. Okay. So, basically if you just look at it objectively, this O is the origin which has a point 0, 0, 0. This is a point which is U V W. Direction is nothing but U minus origin, U V W minus origin basically. Okay. So, if it was x1, x2, x3, if this was y1, y2, y3, then all you need to do is that you need to find out y1 minus x1, y2 minus x2, y3 minus x3, and then convert them back to integers. Alright. So, that will be the direction, because it is a vector, right. So, vector, this is how you draw a vector as you have studied in your school. Okay. So, basically now we will finish this lecture here, and in the next lecture we will look at some more examples of how do we draw the directions, and we will also look at a little different system, which is hexagonal system. In hexagonal system, the directions are and planes can be drawn in a different manner, because depiction of them can be done in 4 digits rather than 3 digits. Because as we will see, hexagonal system can also be characterized by 4 axes, which can be reduced to 3 axes, but 4th axis is drawn just for the sake of convenience, which is nothing but related to 2 axes. So, there is a 3rd axis in the basal plane of hexagonal system. So, we will discuss that in the next lecture. Thank you.